I would like to thank the organizers for arranging this amazing event. Today I'll be talking about new challenges for the world's fisheries. So fish are really the last prolific source of wild food on the planet, and it contributes over $143 billion in global trade. It's also a source of jobs and livelihoods worldwide, and it's a primary source of protein for a lot of people on the planet. All of you probably enjoy seafood, or maybe some of you. And the poorest 1 billion people on the planet rely on seafood as their primary source of protein. So I'm going to give you a background on how our fisheries in the world have been doing over the past half century. The UN has been tracking the status of fish stocks over time, and as you see, as the decades go on, the share in orange of overfished stocks has been steadily increasing. So that's the backdrop of what we're going to talk about today with new challenges emerging from climate change. I'm going to start here in New England and talk about some challenges we're having with productivity, or you can think of the reproduction of fisheries, and how that impacts livelihoods of fishers in New England. And then I'm going to zoom out to look at the globe and talk about how changes in habitat and ranges are interacting with our international policies. And then finally, I'm going to conclude with a story of hope, and that is a policy that is working in the face of climate change for fisheries and what the future of this policy might look like. So to talk about fish here in New England, first I'm going to introduce you to this climate index, the North Atlantic Oscillation. Some of you may have heard of it, some of you might not, but it really is this natural climate signal that controls a lot of what you experience in the winter times here in New England. So it's measured in standard deviations from the mean, and when we get these negative phases of the oscillation, we tend to have colder than average winters in the US Atlantic coast, not just on land, but also in the water. When you get positive phases of the NAO, we get warmer than average winters here. Here's a graph of this index oscillating over time over the past century. And as what you're seeing is towards the end of the time period, the last couple of decades, we're getting very large positive events. So these extremely warmer than average winters in New England. And so how does this affect the fish? Well, this is Atlantic Cod, a favorite species here. And when it first starts out in life as eggs and larvae, this is when it's most sensitive to its physical environment around it. We can actually measure a cohort of fish that are born during a year where we have a positive phase of the NAO index. And we can track how that cohort, that population, evolves over time as they recruit into the fishery, so where they get the most massive die-offs due to natural changes in environments in that first year, and then they become juveniles and recruit into the fisheries where they're large enough to actually swim against the currents. Then at about 3 or 4 years old, they're old enough to be legally caught by commercial fishers. So we can track this cohort of fish through these first 3 or 4 years of their life. And what we find is that when we get a 1 unit increase in the NAO index, or this positive event, these warmer than average winters, we see a decline of 17% of the fish population in the Gulf of Maine. And this decline persists for the first 6 years of the fish life. We see a similar decline in Georges Bank, but it's about half the magnitude, 7 to 8%. So our next question is, does this affect the fishers who fish them? And that really depends on what they fish. So the most numerous people in the fishing industry are the crew, and they're going to move from one boat to another depending on who has a job for them. And the most common species that are caught in New England are lobster, the ground fish like Atlantic cod, and sea scallops. All of these fisheries have a similar reaction to these warmer NAO events, these positive events. They don't like them. They are very reproductive in these negative phases. So we get these booms in the population when we get these colder than average winters. And then there's really no fish in New England that prefer these warmer winters. This is very different from the South Atlantic, which is the range from North Carolina to Florida. We have some warm water species like shrimp and drumfish that really love these positive, warmer than average winters. They have population booms in those times. But they also have some cold species like we do here, like bluefish and summer flounder that migrate all the way from the south up to New England. And they also prefer these negative NAO phases. So we hypothesize that fishers might be able to mitigate these oscillations in the South, but maybe not in New England. So when we take all the catch data in New England and all the catch data in the South Atlantic and look at what's happening to them over time after we get these positive NAO events, we see in the orange that catch is declining for New England and revenue is declining for New England. But in the South Atlantic, in the gray, it's holding steady. So does this translate to wages and jobs? And we find that it does. When you look at the blue dots, this is the decline in wages for fishermen after a positive NAO event that persists for 6 years, about 35% decline compared to fishers in the South Atlantic. We also see a decline in employment of up to 16%. And this, when we look at other industries that shouldn't be affected by the physical environment, such as arts, recreation, finance, tourism, and education, there's no effect of this signal on their wages and their employment. So we find out that the climate, even its variability, has effect on how reproductive this resource is, that then has an effect on our economy. I'm now going to zoom out to talk about another challenge that's facing fisheries, and to do that, I'm going to go across the Atlantic Ocean to off the coast of England and Ireland, where we have mackerel. They spawn off the coast there, and then they migrate in the summers to off the coast of Norway. This is where they feed. Prior to 2006, this has been their migration pattern. And there's an international agreement between the United Kingdom, the EU, Norway, and Faroe Islands for how much fish they're allowed to catch. But due to warming waters, after 2006, their range expanded to off the coast of Iceland. Now Iceland is catching mackerel, but they never caught it before, and they're not part of this agreement. When the other countries asked Iceland to join, they said, we will give you a small share of the fish since you haven't historically been part of this agreement. You can probably guess what Iceland said. No, thank you. We're going to keep fishing. Well, Faroe Islands said, if Iceland's not joining, why should I stick to the agreement? And they started overfishing. So the whole agreement fell apart, and it became known as the Mackerel Wars. We started wondering how many species on this planet are going to move into new national waters due to range shifts. So we modeled this for all the species that we could find data on across the globe. We find there's definitely a poleward movement of these species. So every time a species is crossing into a new jurisdiction it's never been in, it's going to show up as a species on this map. And we have 12 or more species entering new countries towards the poles, indicating there could be more conflict in the future. But what was more interesting is who's losing these species. And we found out that along the tropics, they're going to lose up to 20 or more fish species, and nothing's going to replace them. And this is problematic because the tropics often depend on fish more for food security and livelihoods than other regions, and they haven't contributed as much in emissions to the climate change problem. So we wondered, okay, maybe countries are aware of this, maybe they're starting to integrate this into their international agreements. We collected 127 international agreements with these tropical nations and found that none of them mention these range shifts or climate change or what to do about it. All of them talk about how to maintain and restore fish stocks, which you can imagine you might not have incentive to do anymore if you're going to lose them anyways. So now we're wondering, what should we be doing to conserve this resource? There's discussion of maybe countries that are going to gain the fish stock should pay countries who are losing them to not overfish them before they cross into their borders. And last November, under the United Nations Conference of the Party, they created the first ever loss and damage fund for climate change. And this might be something they will look into to compensate these countries for. Okay, so I just gave you sort of two big challenges and sad stories of the future of fisheries, but there is a bit of hope. There is a policy that is working. So first I want to give you the global context for fish policy to date, and that is under the 2015 Paris Agreement, 193 countries signed on to Sustainable Development Goals. Goal 14 is for life in the water, and one of the goals is to end overfishing and restore fish stocks to healthy levels. This is important because even though we've talked about international policies being important, And even though in the light blue, most of the ocean is covered by high seas, the dark blue is where most of the fish live and where most of the fish are caught. 90% of fish are caught in national jurisdictions. So we need to have countries adopt the goals from the Sustainable Development Goals into their national laws. And actually here in the US, we've done this 20 years prior to the Paris Agreement in 2015 under the Magnuson Stevens Act. So this act has been around since the 70s, but we reauthorized it in 1996 as the Sustainable Fisheries Act. And it has the goal of preventing overfishing and restoring and rebuilding overfished stocks to healthy levels. They do this using science-based thresholds that have been predetermined by biologists, and they update their science regularly to take into account changes to the productivity of the fish or changes to the environment. When a stock is considered overfished, they have these harvest control rules that are very strict that reduces catch until the population is considered rebuilt. The EU adopted a similar law in 2013, but not for full implementation until 2020, which means we have a great natural experiment to see how our fish done with this policy compared to the European Union. So what I'm going to show you here is a graph based on when the stock is considered overfished on year 0. So the year before it's overfished and year -1, we have the biomass or the population of the fish stock. In blue, we have the US populations on average, and you're seeing they're increasing because we're reducing their catch so they can grow back to a healthy level. When you compare this to the EU during the same time period when their stocks go below this overfished threshold, they just sort of steady flat out, but they don't increase because they don't have this law yet. When we compare ourselves to our past before this law was ever put into place in the dark gray, we actually see the biomass of the fish population decline past the overfished level and then continue to decline. So we found that this policy has led to a 50% more increase in fish biomass in the US compared to the EU and doubled our population since the past before we had this law in place. But what's more interesting is that this is happening while we're seeing declines in productivity. So now we're looking at how reproductive these stocks are, how much recruitment they have per spawning biomass, and when their populations decline, we can see in the past the recruitment went up in the dark gray in the United States. This is in the 70s and 80s, before we had as warm waters as we have today. In the EU, we see that the recruitment has kind of remained pretty flat, and the US today in the blue has seen a decline in recruitment. So while we're seeing this massive drop in productivity, we're still seeing this huge gain from the policy. So even though this policy wasn't built for climate change in mind, it's working. So what's going on with the law today? Well, it was last reauthorized in 2006, and Congress has been deadlocked in debate for a decade on how to reauthorize it now. Some believe that it's been too strict a law, that we've done so much to conserve the fish population and overfishing that we're now underfishing. And it's the classic debate of conservation versus jobs. So any bill that has come forward, some believe it's too strict and that it's leading to economic losses for the community and that we need to have less stringent rebuilding requirements, while others believe it's not strict enough and that we should be conserving the resource more. So to sort of help answer these debates, we have a set of papers that we've written that's just coincidentally coming out this Thursday. One is looking at the fishing mortality rate in the US on average for fish stocks before the policy was put in place in 1996. And that dotted red line is the overfishing line. So when we're above it, we're overfishing. And the policy is doing what it's supposed to do, is driving that black line down below that dotted red line and kind of letting it hover around there. For critics who are concerned that we're underfishing, we look at stocks that are underfished in the blue line after 1996, but we found they were actually underfished 6 years before this law was ever put in place. And when we dig into them, they're mostly stocks that consumers are not purchasing. There's not a lot of market demand for them. There never was before, and there isn't today. So underfishing might be happening, but a lot of it is not really due to the policy. There are a couple big exceptions that we make in the paper, and you can look at it on Thursday to see what they are. But on average, the policy doesn't seem to be driving underfishing. And then when we look at the trade-off with the economics, here we're just plotting the average raw data for a stock, and we see in the biomass, that blue line, when a stock is overfished, it's recovering nicely. When we're looking at the catch in the red line, it is declining as the policy intends. But when you look at the revenue in the black line, it's actually held fairly steady. So the trade-off that these fishery managers are making are trying to minimize the economic losses while rebuilding the stock. It seems like the policy is trying to balance the needs of both the conservation of the resource for the future as well as some of the economics. Now, that doesn't mean on an individual level that some fishers are going out of business and some fishers might be benefiting from the policy, but on average, this is what we are seeing. So what does this mean for the future of climate-ready fishing policies? We think that science-based policies with predetermined thresholds are working for biological resources, especially when they take into account uncertainties and have frequent updates in the data and to the science, that there's this sort of nimble process for management to respond to. Where we see the need for more work is on these range shifts. We haven't found great case studies where this is working. If cooperation doesn't work, then maybe compensation needs to be looked at. And this is even happening here in the US as some species from the South Atlantic region are moving into New England, and even states are fighting over how much quota they're getting. All right, so I'll conclude there. Thank you for your time, and I look forward to questions later in the session.